Hi guys, in the last two videos, I've showed that linear regression and logistic regression can also be modeled using neural networks. And that was a way for me to show you that neural networks are not so scary actually, and that there are also neural networks you already know. We just don't call them neural networks. We call them linear regression or logistic regression, but they can also be thought of kind of as a neural network, or they can be thought of in the framework of neural networks. So here, in order to complete the pictures of GLMs, I'm going to show you three other GLMs that can also be modeled using neural networks: the multinomial regression, the Poisson regression, and the gamma regression. And we can use neural networks to recreate the GLM framework exactly, meaning the neural network will have an architecture that will be identical to the model specified in the GLM framework. And it will also have a loss that is equivalent or exactly like the objective function in the GLM framework, meaning it represents the log likelihood or the negative log likelihood, but just use a different optimizing technique. So instead of Fisher scoring in GLM, we will use stochastic gradient descent. But we don't really have to stay loyal to the GLM models. We could use more complex models. So we could use architectures that are more complex, not just one layer that is linear and then some activation function. Maybe we want to have several layers. And also, we don't have to restrict ourselves to the negative log likelihood loss. We can just use any plausible loss function. For example, in the Poisson regression, we could use MSE. Okay, so let's just dive in and start. So in the multinomial regression, it's basically a multi-class classification problem. We assume that our targets, they distribute categorical with C different probabilities, probability for each class. And Y is basically some integer between 1 and C. So it gets 1 if it's in class 1, and it gets C if it's in class C. And there is some constraint here, and the constraint here is that the sum of the probabilities have to sum up to 1. And so there are several ways to model multinomial regression. One of them, which I'll touch upon in this video, is called the baseline or the reference model, where you take one group to be the baseline. So because of this constraint, we don't really need to model each probability on its own. It's enough to model C-1 probabilities. Then the last probability will be equal to 1 minus all the rest. So specifically in this baseline model, this is what we model. This is how our link function is modeled. So the probability of being in some class L, which goes from 1 to C-1. In this case, I take that the reference is the last group, is C. And so the log probability of being in class L divided by being in class C is equal to some linear term. Okay, so some betas that are unique to that L multiplied or dot product times some covariates. And with a little bit of algebra, we can take the exponent of both sides and get this. We can multiply by the denominator to get this. We can use this constraint, the identity, to get this, and then just take the last class and take it to be 1 minus all the rest. We just said that for all the rest, the probabilities are these, so we plug them in. And then we have PCX here and PCX here. We can move this term to the other side, take PCX out, get this equal to 1, divide by this and get PCX equal to this, and then go back here and plug PCX in these equations, and we get this thing over here. So we get one term for the last class, and then a different terms for each of the other classes. And notice that the numerator changes because the BLs are different per L, so per class. But we can also define the betas for the last class to be a vector of zeros, right? Because e to the power of zeros times x is 0, and e to the power of 0 is 1. So we will get 1 here and 1 here. And then we can just model everything. So PL of x as e to the power of this linear term divided by the sum of e to the power of these linear terms, going for all the indices, for all groups. So including group C, and in group C, we will get 1 here and also 1 for the last group here. And so we will recreate this thing. So this is just another way that we can write this down. Okay, so this is what we get, but how do we solve this? Well, there's no closed form solution. We look at the log likelihood and we try to maximize it using Fisher scoring. So how does the log likelihood looks like? Well, the likelihood looks like this: a product over the observation, a product over the classes. For each probability, we take the product of it times the y, where a y now is a one-hot vector. So for each y, we take the different probability. So if for the first observation, let's say the second class was the one that we got in our data, we only take the probability of the second observation. So this whole thing will be just 1p per class, but we don't know in advance, so let's write it like this. Okay, and now we can replace the p's with what we found them to be, and we can take the log of it, and we get this thing over here. And to do the optimization, we need to take the gradients of this, and then the Hessians, or the expected Hessians, and do Fisher scoring. Okay, so this is how we do it in GLM. How would we do it with neural networks? Well, suppose our x's are two-dimensional, and suppose we have three classes, then this is how the architecture would look like, not including another bias term, of course, that goes to all of them. So B1, B2, and B3. Okay, so we will have W11, W21. So this is the linear layer, and the activation function we will use is the softmax. Now, what are the softmax? Suppose that you have x, y, z, and you take the softmax of these three variables, it outputs these functions for each component. So notice that each one of the components has to be between 0 and 1, and their sum is equal to 1. Okay, and also what it does in practice, it really gives almost 1 to the maximum and almost 0 to the other two of the x, y, z here. And this is why it's called the softmax, because it doesn't just take the max. Yeah, the max will just give you 1 for the maximum and 0 for the rest. It gives you almost 1 for the max and almost 0s for the non-max. So it's a soft maximum. Okay, notice that the softmax is translation invariant. Just you should know this. So if we add a t here, yeah, then this just composed to ex et, and we can do the same for here. So we can take et in common out, and then it just cancels here and here, and we're back to what we had before. And this happens also here and also here. Okay, so it doesn't matter if you add a t both to x, y, and z, it will be the same. Okay, so this is the identity that means that it's translation invariant. Okay, the loss that we will use is called the cross entropy loss. It is denoted like this. It's very similar to the binary cross entropy loss from the previous video. Notice that again, it's exactly the GLM loss. It's exactly what we would get from looking at the log likelihood, only again with a negative sign, because we minimize this and not maximize the log likelihood. And the optimization we are doing is stochastic gradient descent as opposed to Fisher scoring. Notice, however, there's 3 different set of betas here, right? So we get B1, W11, and W21 for the first output, B2, W12, W22 for the second output, and etc. for the third output. But in the GLM model, we only had 2 set of parameters, and the other one we just said it's equal to 1. We said that the betas are 0. So we can kind of try to go back by just dividing the numerator and the denominator, for example, here by the first class, let's say. So we would get this, and then from here we will get here, and we can just rename beta 2 minus beta 1 as beta 2 star and beta 3 minus beta 1 as beta 3 star, and then we are getting this. So now we only have 2 sets of parameters, 2 sets of betas or w's, depending on how you want to call them. But as I will show you in the code, this is not exactly what we get. To me, it seems that we are getting some multiplication of these beta stars. I'm not really sure why. If anyone has any idea, let me know in the comment section. So let's switch to the code, and I'll show you how to code this. So I'm importing the same libraries as in the previous video. For the multinomial regression, I'm creating the data almost the same. I'm creating some x's. I'm drawing x's uniformly in a 2D dimension. I'm then adding a column of 1 for the biases. These are my true parameters for this model. Notice that I only give 2 set of parameters, again, because we don't need the third one. Okay, and then I create the logits. I multiply the x's, the covariates, times these parameters. Okay, and now making the denominator what it's supposed to be, and I'm taking P1 to be the baseline class and the others to be the non-baseline class. And I create the p's. And notice that if I sum the p's per row, I'm getting ones. And now I sample from a categorical distribution given those p's. So for each different x, I have a lot of observation, and each observation has a different x. So because of that, we are getting different p's for that x. These p's sum to 1 per each observation. And now I'm drawing from a categorical distribution according to this p's per observation. So for each x, I'm sampling a y based on its specific p's. Okay, and now let's fit a GLM. Again, for stats model, I have to convert this to a pandas data frame. I called stats model multinomial logit. I call fit on that object. And then I'm printing the result. We can see it took 8 iterations. It was really fast. And the results are somewhat close. So remember, we had 0.3, -1, and 2, not quite 0.3, very close to -1, very close to 2. For the second one, we had 2, 2, and -0.3, somewhat close to 2, better, more close to 2, somewhat close to -0.3. So not so bad results. We can also look at the accuracy. So we can call predict on our x's, and this will give us the predicted p's. And then we can decide, okay, which one we will choose. We will choose the maximum. So if we get 0.1 and 0.1 and 0.8, we will choose the 0.8 class. And if we calculate the accuracy, we are getting 86.5% accuracy. Okay, let's now do it with a neural network. So here I'm creating both the linear layer, and it has 2 inputs and 3 outputs. Again, bias is automatically included. If you want to not include it, you have to specify it. And then I do the softmax activation. And I tell the softmax that the softmax is in relation to the columns. Okay, so the rows will be different observation. I wanted to take the softmax per each column. Okay, and then in the forward, I just called softmax on the self-linear of our inputs, and this will give me the predicted outputs. I instantiate this neural network. The loss is the cross entropy loss. Optimizer, I will use the Adams this time. Okay, and now I will train it exactly the same, only I want to be able to visualize the losses. So I will create a list of losses, and then I will append to it the loss from each round. So this is just a simple diagnostic tool that I will use, but of course there are much better diagnostic tools, and this is still a very simplistic way to train neural network. In future videos, we will see the more advanced methods. So let's train, okay, and let's plot the losses. We can see that the losses go very, very fast down, and then at some point we are not improving anymore. And if we now look at the trained parameters of the model, we get this thing. So this is not how our parameters look like in the GLM. But remember, in the GLM, we took the first group to be the baseline. So let's take away the baseline and see maybe now we get something better. And no, it doesn't really look like that. And even if I try to maybe divide it by 3, so this doesn't look like 0.3. This is kind of looks like -1. This kind of looks like 2. This doesn't really look like a 2. This is kind of close to 2. And this does look like -0.3. So we see that we got something that is kind of close to the multinomial GLM fit, to the true parameters. But for some reason, it's multiplied times 3. And as I mentioned before, I have no idea why this is. So this operation is legal. This is translation invariance of the softmax. This is not. So I'm not sure why the neural networks gives us different parameters that are multiplied, but it seems that this is what we are getting. Still, let's calculate the accuracy using the neural network. Okay, strangely enough, it seems we are getting exactly the same accuracy, but it doesn't look like a bug to me. I ran it also a few times before. I got similar accuracies. So maybe in this run, for some reason, we are getting exactly the same. Okay, let's move to Poisson regression. So in Poisson regression in the GLM, we assume that our y's distribute Poisson with some parameter that is related to the covariates. And this parameter, it's also the mean, because the mean in Poisson is equal to the lambda, to this parameter. And the function of the mean is equal to the linear predictor, to the betas times the x's. The canonical and most common link function is the log. So this is the relationship that we have. The likelihood is given by this regular likelihood of a Poisson. And if we take the log of it, we are getting this. If we are plugging this instead of the log lambdas, or the exponent of this instead of the lambdas, we are getting this. And notice that this last term does not depend on the betas. So when we do the optimization, we can just discard it. It doesn't affect the results that we are going to get on the betas. So this is the Poisson regression. How can we do it? How can we express it using a neural network? Well, again, it can just be a single layer with an activation function being the exponent of x. Okay, so the exponent of x just ensures that the output is greater than 0. And so this is what the outputs will be. Again, there is some bias function that also goes here. And this usually goes without saying. The loss, we can either use a custom loss to recreate the same loss as we had in the GLM. So this is the loss in the GLM. This is exactly the y hat that we are now getting in the neural network model. And so here we have a log of it times the y. And here we have just it itself. And we have to have a minus in front of this whole thing. Or we can just use MSE, for example. And the optimization technique is stochastic gradient descent as opposed to Fisher scoring, like always. Let's code this. So to generate the data, I have some true parameters that I'm using, and I'm taking lambdas to be the exponent of these true parameters. And these are the lambdas. These are the parameters of the model. To create the actual data, I'm sampling from a Poisson distribution with these lambdas to get the y's. To do the GLM, I'm converting this to a pandas data frame, and I call statsModel.Poisson. I fit it, and let's print the results. We see again very close to 0.3, very close to -1, very close to 2, and it took 9 iterations, was pretty quick. We can predict using this model. Notice that the predictions here will be a real number, because the prediction only gives you the mean. It only gives you the lambdas. So you can either decide that you are now sampling from a Poisson with those means, or you can simply round it off to the closest integer. Just so we have some measure of how good this fit is, let's look at the mean squared error of our fit. We got 170. The last time I ran it, I got 154. Let's plot the predicted values against the true values and see how it looks. And this is how it looks like. If it was a perfect fit, everything would be on this diagonal line, but it's an almost perfect fit. We see some points are not on the diagonal, but most points are pretty close. Let's do it now with the neural networks. And at first, let's use an MSE loss, so the mean squared error loss. And so I'm just having one linear layer, and I'm taking an activation function to be the exponent of that layer. I instantiate it. At first, I'm taking the regular MSE loss, and I'm training. Let's plot the losses. It looks a bit like this. Let's look at the parameters. 0.3 for the intercept, -1 and 2 for the weights. Let's take the MSE of this, and 165, so even a bit better than the MSE here. But remember, here it doesn't optimize for the MSE, it optimizes for the GLM loss. for the GLM negative log likelihood, or it maximized the log likelihood of this GLM. Okay, so, and if we plot here, we see we also get pretty good results. Now let's try to recreate the GLM loss. If we recreate the GLM loss, it just looks like this. And so I created a custom function that just calculates this. So it takes the outputs of the neural network, the predicted y hat, and the true targets, the true y's, and it calculates this y times log of y hat minus y hat. It takes the sum of it and it takes the minus of it. Okay, the architecture is exactly the same. The loss, I give it this function instead of the NN MSE. Optimizer is the same, and now I'm training exactly the same, only I use this other loss instead of the MSE loss. Okay, let's plot it. It looks like this. 0.5, a bit close to 0.3, but not exact. Close to -1, close to 2. So overall, okay. And the MSE is 464, so a bit worse than the 160, 170 that we got before. Okay, now let's handle the gamma regression. So in gamma regression, we assume that y distributes gamma with two parameters, alpha and beta. And so to distinct these betas from the betas of the coefficients, I will call the beta of the coefficients beta dash. The mean of the gamma distribution is alpha divided by beta. This means that beta is alpha divided by mu, by the mean. The canonical link is the negative inverse, which is this link. But this doesn't constrain the parameters to be positive. So the mean has to be positive. It can't be negative. Yi is, by definition, if it's from a gamma distribution, it's above 0. But here, this, given some coefficients and given some x's, this could be negative. So this could be positive, and then this whole thing can be negative. And this is a problem. So it's better to use the log link. So I'll just use the log link. I'll just take the log of the mean to be equal to the linear predictor. The likelihood, if I throw away anything that is not related to the beta dashes, okay, so we are only interested in the beta dashes. We are only interested in stuff that are related to the mu's. So if I throw away everything else, I'm left with this, the log likelihood. And I can take the alpha out because, again, I'm not interested in the alpha. I'm only interested in the betas, in the beta tags. Okay, so if I optimize this, it doesn't matter that I have some constant multiplication. This is the log likelihood, and I optimize it using Fisher scoring. In a neural network, I will do exactly the same as a Poisson. So I will just take a single layer and take an exponent activation function in the end. And for the loss, I can either recreate the gamma loss like I did here. So this is the gamma loss without the alpha, where I replace e to the power of x transpose beta tag with the output of the neural network. And if I take a minus, then the minuses can cancel and I just get this. And again, I can also just use the MSE. Okay, and the optimization here is, again, stochastic gradient descent as opposed to Fisher scoring. Let's code this. So I'm creating the data here. I'm creating the mu's, and then I'm setting alpha to be 10, and then the betas will just be alpha divided by the mu's. And then I sample from a gamma distribution, giving those alpha and betas. Let's scatter this just to see how it looks. Okay, now to fit it using a GLM, we have to convert it to the pandas data frame. I call statsmodel.glm, and I say that the family is gamma and that the link function I need is a log link function. I fit the model, and if I print the summary, I see it took 15 iterations, and it retrieved the parameters almost perfectly, 0.3, -1, and 2. I can now predict, and I can look at the MSE. It's 46,000 more or less. I can also plot it, and it looks something like this. So we see that it's not a perfect line. If the predicted was equal to the true, we would get everything on this diagonal line, but we see we are getting some deviations from it. We can do a neural network version of it. So it looks exactly like the Poisson, the architecture. At first, I can use the MSE loss and run it. Okay, 0.3 minus 1 and 2, so pretty good. And 45,000, a bit better than the 46,000, but again, this optimizes for the MSE loss, whereas the other version optimizes the log likelihood. Let's plot the predicted on the X and the actual on the Y, and we get a similar graph. And now we can use a different loss that actually recreates the negative log likelihood. And it looks like this. The architecture is the same. We use this different loss. We train it. We plot. It looks like this. Parameters pretty close to 0.3. Not so close as we would want, but at least in the vicinity. Pretty close to -1, pretty close to 2. Let's calculate the MSE. Yeah, 64,000. So a bit worse than the 40-something that we had before in the other two models. Yeah, 45,000. Okay, so let's conclude. Neural networks can create many classical statistical models, some of which you already know. So I showed you linear regression and also logistic regression in previous videos. Now I showed you the multinomial, the Poisson, and the gamma regression. But neural networks can also model more complex structures. The complexity is basically determined by the architecture that you give the neural network. And for example, you can add more layers in the neural networks with more activation function. And in some cases, we don't have to use some distribution assumption. So we don't have to optimize for the log likelihood or the negative log likelihood. We can just use plausible loss function. For example, we can just use the MSE instead of the log likelihood for the gamma or the Poisson distribution. And so this kind of signals a shift from inference to prediction. We just want a machine that can perform well. We don't care so much to understand how it works, how the inputs relate to the targets. We just want it to work. Okay, so I think I had enough with these comparisons. In the next videos, I'm going to go more in depth into neural networks, look how the architectures basically express different function and what is the maximal expressivity without any hidden layer, with one hidden layer, or with more hidden layers. Then look more at how forward propagation and backward propagation works, exactly how do you compute the derivatives in the backpropagation, and look more on how you actually train a neural network and the diagnostics you use, including generalization error, validation sets, and etc. So I hope you enjoyed this video and see you in the next one.